Hello everyone. Welcome to the course Principles and Applications of Mechatronic Systems. I'm your instructor, Jiang Shinjie. Today we'll study Chapter 2, Fundamentals of Automatic Control, Mathematical Models for Automatic Control Systems. The key focus of this lesson is to master the modeling and analysis of mathematical models for automatic control systems. Mathematical models are essential for understanding control systems. I hope you will keep up with the pace, think actively, and work together to overcome challenging concepts. 1. Definition of mathematical model. A mathematical model is a mathematical expression that describes the relationships among a system's input, output, and internal variables. Mathematical models have the following characteristics: similarity, generality, simplification, and accuracy. 2. Role of mathematical models. They facilitate quantitative analysis and calculation using mathematical tools. Modeling provides theoretical guidance for analyzing and designing automatic control systems, and it also offers practical guidance for instrument maintenance, calibration, and the selection of controller control laws. 3. Methods for establishing mathematical models. Analytical method and experimental method. 4. Types of mathematical models. Applying the Laplace transform to a differential equation yields a transfer function. Conversely, applying the inverse Laplace transform to a transfer function yields the differential equation. Laplace transform converts a function of a real variable t greater than or equal to 0, into a function of a complex variable s, defined as follows. The operation of finding the original function f of t from its image function f of s is called the inverse Laplace transform. Quantitative computation in automatic control emphasizes accurate mathematical calculation and is developed based on the transfer function as the mathematical model. 2. Graphical representations of negative feedback control. Block diagram includes setpoint, deviation, control variable, and elements such as controller, actuator, controlled object, and sensor. Transfer function diagram with input R of S, processed by D of S, controller transfer function, K of S, actuator transfer function, G of S, controlled object transfer function, H of S, sensor transfer function, representing signal transmission and control processes within the system. Table of Laplace transform properties, including linearity theorem. The Laplace transform of a linear combination of functions equals the linear combination of their individual transforms. Differentiation theorem. Forms of Laplace transforms for first and second derivatives of a function. Integration theorem. Laplace transform expression for the integral of a function. Initial and final value theorems. The initial value of the original function equals the final value of s times the image function. Shifting theorem. Rules for shifting in time domain and frequency domain. Similarity theorem. Relates time scaling in the original function to changes in the Laplace domain. Convolution theorem. The Laplace transform of the convolution of two functions equals the product of their Laplace transforms. Definition of transfer function. In process control systems or subsystems, the transfer function is defined as the ratio of the Laplace transform y of s of the output variable y of t to the Laplace transform x of s of the input variable x of t under zero initial conditions. Is denoted as g of s equals the Laplace transform of the output variable divided by the Laplace transform of the input variable under zero initial conditions, that is, y of s over x of s. After applying the Laplace transform and rearranging the dynamic equation of a typical process control system or component, the system is transformed from the time domain to the complex frequency domain. This reflects the input-output relationship in the frequency domain and facilitates analysis of system stability, dynamic response, and other characteristics. 5. Common mathematical models in automatic control systems. Typical elements include Proportional element, an element where the output is proportional to the input. Integral element, an element where the output is proportional to the integral of the input over time. Derivative element, an element where the output is proportional to the derivative of the input. First-order element, an element described by a first-order differential equation, commonly referred to as an inertial element. Second-order element, a system that can be described by a second-order differential equation. 6. Block diagrams and their simplification in control systems. 1 definition. A block diagram is a schematic where the text in each functional block is replaced with a transfer function to represent its characteristics. 2 function. When analyzing a system, it is often necessary to perform certain transformations on the block diagram. This is especially important for multi-loop control systems, where the block diagram needs to be gradually transformed into the structure of a typical feedback system. By obtaining the overall transfer function of the system, further analysis can be carried out. 3. Basic connections and rules. Series connection, parallel connection, and feedback connection. Let's look at the basic connection types and typical transfer function formulas. Series connection. The output of the preceding component is the input of the following one. The total transfer function is the product of the individual transfer functions. Parallel connection. Inputs are the same. The total output is the algebraic sum of the individual outputs. Feedback connection. The output is fed back and added to or subtracted from the input. Typical system transfer functions also include closed-loop transfer functions under input and disturbance conditions. That concludes this lesson. Thank you for listening. See you next time.